So welcome everyone. Today we're speaking to Professor Amit Gefen from the Department of Biomechanical Engineering at Tel Aviv University. Really excited to welcome you here, Amit. And today we're really going to talk about your research and highlight what you've been doing over a number of years now. Professor Gefen has been using the Simpleware software for a number of years, and we'd like to highlight the use of the Simpleware software and also how it's helped you in your research, if that's all right. So welcome, Professor Amit Gefen. And just to say thank you again for joining us. It's really nice to have you here with us. So I'll start the interview that we're giving today with my first question, and that's really if you can begin really with telling us a bit more about yourself and your career to date.
So thank you, David, for the introduction and for the opportunity to speak today. Really delighted. I'm a professor of biomedical engineering, focusing on biomechanics, as you've mentioned. My basic science interest is in looking at how cells and tissues respond to mechanical loading in health as well as in disease states. But the applications of my research from a translational science or an applied science perspective are in understanding why injuries and wounds happen and how we can prevent injuries or wounds, or where we cannot prevent, repair tissue or heal those wounds. And for that, I've been using for 2 decades now, a little bit longer even that, an integrated approach that combines together experiments in living model systems, and these living model systems can be, for example, cell cultures or tissue engineered constructs, or even human subjects, with computational modeling for either extracting some more information from the experimental work that we're doing, or for understanding phenomena that are very difficult to analyze when you just do empirical lab work or clinical work. And that's why computational modeling became very early in my career a fundamental element in my research, looking at both how tissues behave and how devices apply to tissues, medical devices or non-medical devices, but devices that are aimed to protect the skin and the tissues behave, and most importantly, how they behave in interaction. So you can think about as a simple example of a dressing, a wound dressing applied onto a wound, or a support surface, such as a mattress or a wheelchair cushions. If you want to prevent a chronic wound, you need to understand how tissues would respond to sitting on the wheelchair cushion for long times, or lying on the mattress for long times. And for that, you have to model in a computer environment the human body or parts of the human body and the support surface and represent them in realistic terms. And I found the Simpleware software package very effective in doing that. And as you've mentioned, I've worked with the software suites in its evolution from one version to another for many, many years now. And with many different grad students and engineers working in my group, my team, using it over the years, all of them told me that it's very user-friendly, easy to work with, and makes very complicated problems such as those that I've just mentioned easier. I'm not saying easy, but easier to handle.
Sure, it's really good to hear. Thank you for that feedback, and it's great that it's helped you so much throughout the years, and to have that sort of feedback is wonderful. And what you've said, so obviously your research has been focused on the interaction of tissues, human tissues, and devices or support structures for helping people. And your research has focused on recently things like heel ulcers and pressure ulcers, and also characterization of foams in those support structures. Where is your focus at the moment? Are there any interesting examples you're working on currently?
So how can we not speak about COVID?
Exactly. Yeah.
So although Israel and the UK are not doing bad at all in terms of the vaccination programs, the rest of the world is still heavily impacted by COVID. And COVID means a mass of people undergoing intensive care in intensive care units. And with those people needing intensive care, the critically ill COVID patients, they use devices for different life supporting functions attached to their bodies. Starting from ventilation equipment, CPAP mask, endotracheal tubes if it's an invasive ventilation, monitors, electrodes, sensors, anything that can touch your body, that touches the skin, that contacts the skin. When you're unconscious or sedated, and under these hectic circumstances of an intensive care unit, people tend to develop what we call medical device-related pressure ulcers, which are pressure ulcers caused by the medical device that fulfills some kind of function related to ventilation or nutrition or monitoring the patient. But at that time, when it contacts the skin and applies forces on the skin, and the person is not in a position or not in a state to complain about discomfort and pain because they can't feel it or they can't communicate it, and the device injures the skin, that can range between unpleasant to very dangerous. I just need to remind people that any breakdown of the skin happening in an infection-rich environment such as a hospital calls for pathogens to penetrate the body. So the last thing that you want is skin breakdown. And indeed, we are seeing many or much more than what we've used to see in terms of prevalence and incidence of pressure ulcers. And we need to understand what is it about these devices, especially with COVID, that causes these tissue injuries. And this has been the focus of much of my recent work in the last year, also employing Simpleware to reconstruct, in a computer environment, to reconstruct the scenario of, say, the head of a person with a ventilation tube, with an endotracheal tube inserted, and reconstruct these scenarios where the tubing is causing a pressure ulcer to the lips and to facial tissues, very common nowadays, leaving, even if the person recovers from COVID, leaving facial scarring, and consequences related to body image that will accompany that person for the rest of their lives.
Yes. Yeah.
Same thing with CPAP masks, which are now becoming very popular in supporting breathing functions of people with respiratory distress syndrome, which is part of the disease, the symptom of the disease. And then you put a CPAP mask, and that CPAP mask is being strapped really well to the face to prevent leakage and deliver the oxygen that it should deliver. But again, these patients are not fully conscious. Their sensation functions are not are often impaired because of medications or other circumstances. And then you see these awful pressure ulcers on the face, breakdown of skin on the nose, and the chin, the cheeks, leaving facial scars forever. And that's what we're trying to prevent. And for that, you need to really understand the anatomy and the physiology of the tissues and the construction of the device, I did not find a better tool to characterize these geometries and the complex contact interactions than Simpleware over many years, as I've mentioned.
We're glad it's helped you so much here, especially in these very hectic times. If we can help you to have this positive impact, it's wonderful. And so you talk about the CPAP mask and its potential to create these pressure ulcers, facial pressure ulcers. What are the sorts of strategies that you've foreseen and solutions you've been able to determine from your use of the software for biomechanical engineering of the facial tissues?
It's a good question, Dave. So at the beginning of the pandemic, I've been approached by several health organizations with requests for recommendations and solutions here and now, not in 5 years, not in 10 years, which we academics are used to deliver. That's the we do research, so we look at 5 years ahead. But these clinicians taking care of masses of patients needed, solutions right here, right now. One of the things that we have examined using computational modeling approaches is to use dressings, wound dressings, prophylactically, that is for prevention, as opposed to a dressing that you put on a wound where you have a wound. You cut a piece of the dressing, you put it on your face, at the bridge of the nose, the cheeks, the chin, the sensitive areas, and then you tie up the mask, and then you have a cushioning layer. But it turns out that it's much more than cushioning. You need to make sure that you absorb as much of that mechanical energy and you kind of distribute it so that you don't get these stress concentrations in the tissues. And more complex dressings in terms of the material behavior are rather effective in doing that. Again, depending on the specific, as you were saying, you referred to forms. So if we think about foam dressings, and a lot of the advanced wound dressings are foam dressings. If you think about forms can be very different from each other, right? Each has their own density, stiffness properties, strength properties. So we really developed a robust, very powerful approach to assess which dressings, which specific products that could be bought off the shelf and again, applied here and now to protect the face. And we have published the work, and very quickly that has been adopted in many centers around the world in terms of selection and application of prophylactic dressings for protecting facial tissues when you use a CPAP mask. And that's just one example. There are other examples for protecting other areas of the body. So for example, if CPAP doesn't work or doesn't work sufficiently and oxygen levels still drop or remain low, there's no choice but to intubate and ventilate mechanically in invasive ventilation. And one of the clinical practices that before the pandemic has never been used in such an extent, in such big mass, is to ventilate people where they're prone, they're lying on their belly, as opposed to the conventional ventilation, which is supine. So you lie on your back, the head of the bed is tilted a little bit. And it turns out that lung function is improving to some extent when you ventilate people prone. There has been clinical experience with that, but not at the numbers that we saw in the last year. But then when you're proning somebody, the weight of their own body is on the face, on the forehead, the chin, the chest. You don't have a lot of soft tissue here. You don't have a lot of padding. So another practice that we've helped develop was to use dressings when you do that. Again, saving people's skin from breaking down after 12 or 18 hours in a prone position where you can't move and you can't feel, essentially, because you're anesthetized for the ventilation. And again, that proning practice, which has really been brought to the extreme, required new bioengineering knowledge, not in 10 years projects, but right now. And we have delivered that, and your products have played a role in that, and I appreciate that.
It must be enormously satisfying to have that immediate impact into people's lives, essentially, and in an important area that's not necessarily the addressed immediately. The immediate requirement is to save this person's life from this terrible virus and help deliver oxygen to them, and everything else may fall away in the periphery, but then being able to stand there and say, this is really, really important. This person, getting through this person is going to have enormous difficulties if we don't do something now. And
Correct.
It's amazing how quickly it can develop this, the problems that you focus on treating and developing treatments for, if it's not thought about immediately. In terms of that, so, obviously the world has changed dramatically in the past year, and the focus of your efforts, I imagine, have changed quite dramatically, although the subject is the same, where the applications are the people that you're treating necessarily, or that you're developing treatments for, that's changed significantly. Do you see, has that changed your long-term plans for your research dramatically, or are you still aiming for the same topics that you were thinking of addressing a year, 2 years ago?
Well, there are so many layers and aspects from which I can answer your question. So in terms of how I work, you know very well, David, that I used to live on airplanes, and I've never been to. I did not visit an airport or been to an airplane since March last year.
Like many of us.
Like basically like all the rest of us, yeah, right. But that has brought the opportunity to be anywhere, anytime. So this morning I've been to the UK, and then I've been to Sweden, and now back to the UK with you. And this is like a typical day, and it will go on and on with the US coming later on in the day. And that has brought the opportunity of really getting immediate feedback, not once in a year when you go to that specific conference. I'm speaking with my colleagues and co-workers and friends around the globe almost daily now, in a different way than we used to, because it used to be like, let's wait for that conference when we meet and we speak then. So I think that one thing that the pandemic did to science in general is that it sharpened our global communication skills in using these virtual tools. The other thing is that what I did during the pandemic in terms of the computational modeling work cannot be separated from everything that I did before that, in the sense that it all builds on the etiology and really understanding the damage processes from the cell to the tissue to the organ level and to the body level, which I've done for many, many years, using your software and other software packages when I do my computational work. But it's that understanding that allowed me to kind of innovate under these extreme conditions, which require, of course, extreme measures, but innovate very quickly and move very quickly towards a solution because of all that basic science work that has been done previously. So it's like building a tower. You always have to lay a very strong foundation if you want that tower to last for a long time. And we have, in terms of preventing chronic wounds or treating them effectively, have put very strong foundations in the ground, and that allowed a lot of the innovation that we have introduced during the pandemic.
And are you seeing some applications ahead of us, coming that we're not necessarily seeing at the moment, but long term, some challenges that are approaching?
So again, just using the examples that I gave already. So there are two strategies. One was to find a solution right now, but the other is to now revisit all these design of medical devices that are causing pressure ulcers, and also think about whether there could be other materials, smart materials, and structures that are not necessarily dressings, that can protect patients long term and way after this pandemic will end, because the virus is going to run its course at some point. It has probably already in Israel, but globally that will happen as well. But people will still suffer from pressure ulcers, body weight related or device related. And we really need to think of all the knowledge that we've gained as a way of revisiting the design of devices. And again, computational modeling is going to play a very, very important role in that. Because what is more straightforward and more easy to apply than having a computational model that is robust and you can change material, stiffnesses, and other characteristics to get almost immediate feedback on the tissue loading state when you change something in the device or in the interface material under the device to mitigate the load, to alleviate the load, and you adjust those parameters in the computer, and you almost immediately get an answer which without computational modeling would have taken years and years and years of building prototypes, manufacturing them, applying them, measuring something in a patient or in a dummy, and going back to the manufacturing process and readjusting and redesigning and all of that. Computer modeling has shortened that process so much and made it so effective that I think that this now prepares the ground for totally revisiting, again, something which is only being possible because of now understanding, our current understanding of why pressure ulcers happen and how they happen. Doesn't really matter if it's a device-related pressure ulcer or body weight-related pressure ulcer. But now that we understand how they happen and why they happen, we can change those device designs so that they contain better materials at the interfaces with skin to prevent these injuries.
So on that note, I think that's a fantastic note to end the interview. I mean, the requirement for biomechanical or computational biomechanical engineering is clear, and how it's going to help everyone in the future. So I'm enormously grateful to you, Amit, for joining me today for this interview. Thank you very much. It's been really interesting speaking to you about your work and research and the applications onward and upward. And it's really good to be a part of it. So thank you very much.
It has been a pleasure, David.
Likewise. So for everyone listening, to let you know, Professor Amit Gefen will be talking in more detail about all of these subjects on the 23rd of June, where we will be holding a webinar together, and Professor Gefen will be running through some examples to show you more about his research topics and to delve into more detail there. So thank you once again, and looking forward to speaking to you then. Bye-bye.